Thank you. Yes, so it would be me. Can you hear me? Is it okay like this?
Yes, sir.
Okay, thank you very much. Thank you for the feedback. So I'm very happy to participate again at this conference. So this is my second year here. And as Katarina in the previous talk, I will also speak about a numerical method and convergence analysis. So precise error estimates, which I won't prove, of course. I will just show some ideas. So first of all, let me mention that this is, of course, a joint work with Bálint Farkas from Wuppertal and Balázs Kovács from Regensburg. And this is already submitted to the Science Journal of Numerical Analysis. So just let me hide myself and these things. Yes. So the outline of my talk. So first of all, of course, I will talk about what boundary coupled system mean. Then I will talk about a little bit about operator splitting procedures, because I will apply this in order to introduce this numerical method. Then I will show the numerical method itself. And I will speak about the convergence analysis, or at least the idea of the proof. And at the end, I will show the numerical experiments done by Balázs Kovács, my co-author. So let me mention that this is a continuation of my talk from last year. So let me just show this here. This is a continuation of my talk from the last year, from linear case to the semilinear case. So this is important here, that this is now a semilinear boundary coupled system. So what do I mean on that? What is a boundary coupled system? So as a motivation, just let me show you, this is a tissue with some cells here inside. And we all know that some processes are going on also inside the cell and also outside of the cell, and they interact somehow. So this is now models of this cell. So this is a domain omega, and we know that also inside of this omega we have some kind of differential equation. It can also be some nonlinear operator, and on the boundary we also have another differential equation, and then the coupling between them is the boundary condition. This means that the inner solution is always the solution to the problem on the boundary. Okay. So the idea is how to solve this problem. Is the idea to solve the problem separately. So the idea is to first solve the problem on the boundary, this on the boundary. Then we have V of t, and this is the boundary condition. So this V lives on the boundary, and then we have the boundary condition for the inner problem, and then we solve the inner problem. So this is on d omega, we have the boundary condition, and then on omega. This looks a very promising idea. However, when doing the numerical experiments, it turns out that it is wrong. I will tell you what does it mean wrong, because we will have some kind of numerical solution, of course, but it turns out that it doesn't converge in the expected order. I will speak about this. I will define what it means. So we need some modification, and this is the question, how to modify this idea. In order to do this, first, I just hide this also here, sorry. So first, I introduced the semilinear boundary coupled problems. So first we have two Banach spaces, and then we have an abstract Cauchy problem on the Banach space E and also on the Banach space F. So you can see that this will be some kind of function space of functions on omega, so the inside functions. And these some function space on the domain somehow. So for an example, so this is just an example. And we have some coupling between these two abstract Cauchy problems. These abstract Cauchy problems are semilinear Cauchy problems. So these are linear operators. These are the linear parts. And here with blue, we have the semilinear part. So F could also be a nonlinear function. F1 and F2. And we have, of course, the initial data for the corresponding problems. So as an example, as I told you, consider that omega is a bounded domain with some smooth boundary, d omega, and then also E and also F are the corresponding L2 spaces. And the operator A is the Laplacian inside omega. So this is the Laplacian we all know. And the B is the Laplace-Beltrami operator on the boundary. And L, so this coupling operator, this is just a trace operator. This example defines a diffusion also inside omega and also on the boundary. And Vt is really but the boundary value of U of t. This is just an example, but if we have some broader assumptions, then L shouldn't be actually the trace operator. So let me list you the assumptions only on the linear components, on these red A and B operators. They are linear operators. L, the coupling operator, is also linear. This is surjective and bounded with respect to the graph norm of A. And which is very important that the B generates an analytic semigroup. Actually, in our proof, this was just a simplification in order to have, let's call it simple proof. Actually, we don't really need this analyticity of the semigroup, but we could show that we cannot have better results also if B is not a generator of an analytic semigroup. This A, so instead of A, we now consider this A naught, which is the part of A to the kernel of L. This also generates an analytic semigroup, and this is really needed in the proofs. And this is just a technical assumption. Actually, I told you that this is a broader assumption. So this means that in this context, one can also treat that delayed differential equations or also dynamics on networks. So if you choose well these operators and spaces, then we can also handle these problems. So this was only the linear part. So let me see what we have to assume for the semilinear components, so for the blue F components. So first of all, this F, which is the F1, F2 function, it should be Lipschitz continuous on the strip. This is a strip around the exact solution. So what does it mean? This means that we have some kind of exact solution. It looks like this. So well, now in one dimension, so you can understand what it means. And then this R means that we have a strip around this exact solution, of course, in the function space and not on the plane, but you can understand. So this is somehow R. And when we are living in this strip, then this F is Lipschitz. Also, F2 should be Lipschitz. That F of U should be differentiable and the derivative should be bounded, also should be in L1. And these are actually technical results, but they are a little bit strong, but there are a lot of examples which fulfill these assumptions. So the boundary solution, the solution on the boundary should be in the domain of B squared, but also F2. So this is not so strong, but F2 of the exact solution should be also in DB squared. And the corresponding values should be bounded. So let us see what can we do with these problems, how to solve this problem. Of course, we need to approximate the solution of this problem. We need to find a numerical method. So this is our aim to get. In order to do this, we need an abstract Cauchy problem. We would like to reformulate this problem or these problems into only one abstract Cauchy problem. How to do this? In order to do this, we introduce these boldface A operator. This is actually an operator matrix. This A and B matrices, they are the same as before. So these red matrices, operators, and this operator has then this domain. So this means that here we have the coupling in the domain of this boldface A. So this coupling is there inside the domain. So this is like a boundary condition when we are talking about really partial differential equations, how we rewrite them into abstract Cauchy problems. Then our boundary coupled system looks like a semilinear abstract Cauchy problem in this way. So here we have this U is of course the vector valued function uv, small uv, and f is f1 and f2, and then here we have this operator matrix and the semilinear function. And the initial datum is of course consists of the two initial data, and then sorry, we don't need this anymore because it is already there. Then we have this theorem stated in 2003 by Casalino, Engel, Nagel, and Nickel, who said that operator A generated a C0 semigroup, which has this form here. I will talk about this, where this D0, which is here, D naught, this is the inverse of the coupling operator on the kernel of A. So this can be also called as the abstract Dirichlet operator. Then we have this semigroup. So this is very important that here in the left upper corner, we don't have the semigroup related or generated by A, by the semigroup generated by A naught. Here, A to the semigroup generated by B is okay, and this Q of D, this blue one, is defined here. Here now in the talk, this form is not really important. In the proof, of course, this form was very important. Therefore, I wrote this on the slide. So this is our main theorem, which we use in order to prove our main theorem. How to formulate, how to define a numerical method from this abstract Cauchy problem. So first of all, we rewrite we can write the variation of constants formula, and then we have the exact solution to this problem. Then we choose a tau. This is like a time step. We can call it a time step. This is just a positive number, and then after a small short reformulation by using the additivity of the integral and the linearity of the semigroup and the integral, we get this form. This is exactly the same. This is just a variation of constants formula. But now, here is the question, how to get these semigroups? Because when we are really using computers, we don't have these semigroups. We need to approximate also these semigroups. How to do that? Let us observe that this boldface A operator matrix can be written as this product of these three operator matrices. This was also observed first by Casalino, Engel, Nagel, and Nickel. And here what is very important, that this curly R operator is here. Here we have this abstract Dirichlet operator and the identities, and here it is just the inverse of it. So this looks like a diagonalization. And here in the middle, it is very important. In the middle, this operator matrix, this can be split into the sum of three operator matrices. The blue one only contains A naught. The red one only contains B. And in the middle, we have this, well, disturbing term on the right upper corner. Now, the semigroup generated by this boldface A can be written, of course. So here I just wrote this is boldface A. So here I didn't do anything. I just wrote this form here. The question is how to approximate this semigroup. First, we assume that all of these colored operators are generators of C0 semigroups, and then this approximation, of course, it needs to be satisfied, but this is actually, yes, like a Trotter product formula. This can be approximated, but of course, this is to be proved in all of this setting. So now, so what we have here is that this semigroup is approximated by this S of tau, where this, all of these is S of tau. What to do with this? So what does it mean? So this means that instead of the whole effect of this A plus B plus C, first we have only the semigroup generated by C, only the effect of the physical process which is described by C. Then only after that the effect of B, and only after that the effect of A. So this means that as if the physical phenomena took place one after the other in time, and not simultaneously. Just an outlook as other examples. So this is what we call operator splitting. So this is just an example to operator splitting, because you can see that here we split one operator into three, and then also the semigroup was approximated by this way. Also, attraction diffusion reaction problems can be treated in this way, or something like physical problems with dynamics and some control or potential. So always when you feel that there is some kind of sum in the physical phenomena, then you can split them together, and computationally, numerically, it is easier to treat them like that. In our case, what to do with this? Now we have two approximations. So here, I don't have any approximation yet. This is just a variation of constant. We have seen that. The first approximation is because of the operator splitting, or done by operator splitting. So the semigroup operators are approximated by these red S tau operators. But then here we are left with this integral. We also need to approximate this integral. How to approximate this integral? For example, we take the integral at 0. Then, yes, we have, this is the length of the interval, and S equals 0 also here, and also here we have this blue term. You can see that S of tau appears in both terms. So this is our approximation. This is our numerical method. A numerical method is not defined by an approximation sign, but of course we need some equality. So the numerical method is defined as follows. We have some time step tau, and then for all steps, for all n integers, this is the notation. So the exact solution is approximated at n times tau by u sub n, and here this tau means here in the top that it depends, of course, on the choice of tau. And then this is the numerical method. Here we have the initial data, and this is the numerical method. So for example, the value at the nth time step depends somehow on the value of the n minus 1st or first time step value. So this is like a one-step method. So this is our numerical method we are dealing with. This is what we are analyzing, and we would like to show its convergence and also the convergence rate. I have to call your attention that now, instead of a continuous function, the numerical method only gives some discrete values in time. So this is like 0, tau, 2 tau, 3 tau, and so on and so on. So how to define the convergence? So here we have the same figure. This is the numerical method. The question is, will the approximation be more accurate where the resolution gets finer? So this means actually when tau tends to 0. So here, look at this picture. You can see that here we have this t, time, for example, and this is the error. And the question is whether this error will be smaller when the resolution gets final. Yes, you can see that this is just an animation, of course, this is not a real result. This is to motivate why we define the convergence as now. So the definition, the numerical method is called convergent at t time level if this limit is 0. So this means that these points converge actually to this continuous exact solution when n goes to infinity. And the method is called convergent of order P, and this is what we saw also in the last the previous talk by Katarina. So the exact solution minus the numerical solution. So here this norm, the norm can be estimated by a constant over n over this P, and this P is then the order. So let us see what we have proved. We could prove that this error can be estimated by a constant times the logarithm of n over n. So this log n doesn't play really an important part here because n goes to infinity, and then this will be a first order method actually. So this is what we have proved, but how? This is the question. So this is actually part of the convergence proof. This is of course just I took it here only for fun. The idea was to write the error. So this was the error. So inside the norm, so the exact solution minus the numerical solution as the sum of some sub-errors. And then we obtain a recursion with the past values of this error. We solve the recursion, and then in the recursion, in the solution of this recursion, we have some error terms, and these error terms we have to estimate. So more precisely, this looks like this. So here we have the global error. Here we subtract and add the numerical method at the previous time step. And then we just reformulate everything. And here we have now, this is what I would like to do, like this, the local error. This is the propagation of the global error of yesterday. And this is the propagation of the error of this f function. So we can resolve this recursion, and this will be the solution. So here again, the first term is the local error. The second term is the sum up, when we summing up the local errors in the past. This is the sum up of the errors of this f function. And this is the error of the initial datum, which we assume to be 0. And now our task was to estimate these 3 terms in norm. And this was really like 3 pages or more. So this is I of course don't want to show you now in details. The main tools we used that the abstract dictionary operator is bounded. Of course, as in any convergence proof, also in one dimension or in R, we use that the Taylor formula looks like this, for example, or also for the higher order terms, also for the second order terms. We use that this A node that generates an analytic semigroup, and therefore we also have this estimate, which is very important in these proofs. And for the semilinear part, the Lipschitz continuity really plays an important role, not only for F, but sadly also for F2. Why I said sadly? Because we had an example in mind where this F2 was not Lipschitz continuous. So this is our next aim, to somehow weaken this Lipschitz continuity condition F2. So in order to show you some numerical experiments, so this theoretical part ended here, so this, and now some kind of illustration, so what we had in mind. So we had in mind, for example, that here we have a diffusion inside omega and also a diffusion on the boundary. And we have some kind of F1 and F2 functions, something. Why exactly this and what are these row functions? These row functions are chosen such that we know the exact solutions. So this is very important. So this is just a test example, but here we have the known exact solutions and therefore we can compute the error really explicitly. So this is the well, this is a little bit funny, but this is the exact error. So now we can really compute this and we get these error plots. But here we need to see that this is here the slope 1 line, and we also need to have a first order method. So therefore this is the logarithm. So this is a logarithm log plot, the step size and the error. So the first order numerical method means that these dots are lying on a almost straight line, which is first order. So this is has a slope 1. This is what we needed to see. So this is for U and this is for V. And here the lot of dots correspond to these. So these are the delta X, so to say, so the spatial discretization grid size. So we needed to discretize with finite element methods also these Laplace operators. And here we have more and more grid points. And you can see very well that when it comes finer and finer, then it really has a nice slope. It's even better, actually, as slope 1. It's even better. Well, it's very promising. So I just made here a check mark. So this was really an example which fulfilled the assumptions. But we also had an example in mind, which I told you that it doesn't fulfill the assumptions because this here, so this F2 is not Lipschitz continuous. However, we made the same numerical experiment with the same method we introduced, and we saw also a very nice order plot. So this is a very promising result because this means that the method we introduced works well also in the non-Lipschitz case. We just don't know how to prove it yet, of course. So maybe next year on the next OPSO conference, I will report on our success. I hope so. So as a short summary, I just say that we invented new numerical method for semilinear boundary coupled systems, which applies operator splitting, and this numerical method converges of the expected order, which is now a first order. So we don't have any order reductions. We also couldn't see it during the numerical test. So everything works fine. And we could also show that at least numerically, it also works for so-called dynamic boundary conditions, which is a not Lipschitz case. So this is the end of my talk, and I thank you very much for your attention.
Thank you. Questions for speaker? No? Okay. Next.
Excuse me, may I ask?
Oh, okay.
Hi, Petra.
Hi.
Thanks for the nice talk. I wanted to ask, is it possible to, so now in your system you have like a PD in a domain and then the other thing is on the boundary of the domain, but is it possible to apply a similar approach if you have two domains, but they share a boundary?
Yes. Actually, the main motivation was this case. We wanted to solve this case, and then we reduce to that one, but we have this in mind. So therefore, I cannot answer to you, but I think that yes, so this would be the main aim of that. So we, yes, as you thought, so we have, yes, one domain, and either we have some outside domain, or we really have two domains, like you said, and then we have here something. Yes,
so then you have just like a matching of two boundary traces from the two domains.
Yes,
so
yes.
Okay, great. Maybe next year in the OPSO.
Yeah. Thank you. I hope so.
Yeah, thanks.
Thank you.
Okay.
Maybe I can also ask a question. At the beginning, you said that analyticity, that you added analyticity for the proof, but that you actually get the same results for non-analytic semigroups. And my question is somehow the other way around. So if you assume more on the semigroup and on the semilinear flow, can you expect to have higher order convergence, or is that out of reach?
Okay, so now I really have to think about, no, we cannot have higher order convergence in this case, because in this case, this operator splitting itself was a first order operator splitting, and also when the integral was approximated, well, not a sum, but when s equals 0, this was also a first order approximation. So now we cannot get, but we are working on a second order scheme now, so a second order scheme, but now with another operator splitting procedure. So not with this trotter-like, but the so-called strength splitting, which is itself a second order splitting, but then we also need a second order approximation for the integral. And we could almost show that
Okay.
we need something there, just one little term, but this will be a second order scheme, we are almost sure. And we also have the conjecture that in this setting, we cannot have better. So when using these steps of these ideas of the proof, we cannot have higher order than their second order.
Okay, thank you very much. And
Thank
also
you.
thank you very much for the interesting talk.
Thank you.